Hello. Recall that in the previous lecture we discussed different measures such as egress filtering and distributed route filtering. These were measures to prevent distributed denial of service attacks. Now we discuss some techniques that can be used to detect distributed denial of service attacks. So egress filtering and DRF are preventive measures. An alternative approach is we detect the onset of denial of service and then take remedial action. So that is we detect denial of service attacks. So recall that a TCP connection is initiated by a three-way handshake in which SYN, SYNACK and ACK packets are sent. Later on, the TCP connection is closed by each side by sending a FIN packet which is ACKed by the other side. So for legitimate connections, a server receives SYN packets and FIN packets in pairs. That is, for every SYN packet, it eventually receives a FIN packet. So the number of SYN packets and FIN packets should be roughly equal. But in a SYN flood attack, the victim receives much larger number of SYN packets than FIN packets. So recall that the attacker just sends a SYN packet and then does not send subsequent packets. So the connection is only half open. So in this case, the FIN packet is not sent corresponding to a particular SYN packet. So hence, in a SYN flood attack, the victim receives much larger number of SYN packets than FIN packets. So this fact can be used to detect SYN flood attacks by a victim, as we now explain. So the idea of this scheme is we keep track of the number of SYN packets received and the number of FIN packets received in an interval, and they should be roughly equal. So if the difference between SYN packets and FIN packets exceeds the threshold, then that is an indicator that there is probably some SYN flood attack ongoing. So this figure shows two horizontal timelines. This is the SYN timeline. So this shows the times of SYN packet arrivals. So these arrows, they are instants when SYN packets are received by a particular host. And this bottom line shows the corresponding FIN arrivals. So these arrows show the time instants when FIN packets are received. And notice that there is a correspondence between SYN packets and FIN packets. So for example, first a SYN packet is received for this connection, and then this is the FIN packet for the same connection, and this is a SYN packet for this connection, and this is the FIN packet for that connection, and so on and so forth. Time is slotted into fixed length observation intervals. So on the SYN timeline, these intervals are T1, T2, T3 and so on. And on the FIN timeline, there are corresponding observation intervals T1 prime, T2 prime, T3 prime and so on and so forth. So these observation intervals are T1, T2, T3 and so on the SYN timeline, during which we record the number of SYN arrivals. And the observation intervals on the FIN timeline are T1 prime, T2 prime, T3 prime and so on, during which we record the number of FIN arrivals. So notice that the observation intervals on the FIN timeline are shifted to the right by some amount relative to the SYN timeline. So for example, this observation interval is shifted by some amount relative to this observation interval. This observation interval is shifted to the right relative to this observation interval and so on and so forth. So this shift amount is the average duration of a TCP connection. Hence, if the SYN packet for a particular connection is received in a particular observation interval on the SYN timeline, then the corresponding FIN packet should be received with a high probability in the corresponding observation interval on the FIN timeline. So hence, the number of SYN packets received in this observation interval in this timeline should be roughly the same as the number of FIN packets received in observation interval on this FIN timeline. But the number of SYN packets and FIN packets in a particular observation interval are only roughly equal, because the durations of different TCP connections are different in general. Not all TCP connections have the same duration. So it can happen that if there is a long-lived TCP connection, then the SYN packet is received in this observation interval, but the FIN packet is received much later in some subsequent observation interval. So hence, we can only roughly say that the number of SYN packets in a particular observation interval on the SYN timeline should be equal to the number of FIN packets in a particular observation interval in the FIN timeline. So to construct an anomaly detection system, we define the following variables. SI is the number of SYN packet arrivals in the ith observation interval, and Fi is the number of FIN packet arrivals in the ith observation interval on the FIN timeline, and Si is on the SYN timeline. Define Di to be the ratio Si minus Fi by Fi. So if the number of SYN packets and the number of FIN packets is the same, then Di will be 0. When a SYN flood attack happens, then Si will be much larger than Fi. So Di will be a large positive amount. So that is what we have to detect. If Di is close to 0, then it is normal operation. But if Di is a large positive amount, then it is indicative of a SYN flood attack. Let tau be the threshold for detection. We design different algorithms to detect the onset of a SYN flood attack. Consider the following time series, D1, D2, D3 and so on. So we will discuss different algorithms that attempt to detect the onset of a SYN flooding attack by monitoring this time series. If many of these DIs are large, in that case that is indicative of a SYN flood attack. So DI is large does not always mean that there is a SYN flood attack, because there is some randomness in SI and Fi. So we know that Si may not be equal to Fi since the durations of TCP connections are random. But if a lot of consecutive DIs are large, then that indicates that with a high probability there is a SYN flood attack ongoing. So that's what we have to design algorithms for, to detect whether there is indeed a SYN flood attack that is ongoing. So in the first algorithm, we raise an alert if the most recently computed decision variable Di exceeds the threshold. That is, if Di is greater than some threshold tau 1. So this upper figure shows the operation of this algorithm 1. Di is plotted on the y-axis and the x-axis is time. So we can see the variation of Di. It is always above 0, and the threshold tau 1 is 90, so that threshold is shown here. In this time interval, at this time instant, Di exceeds the threshold 90. So in that case, the algorithm raises an alert. So at this instant, it raises an alert. In this instant, DIs are very high. They are close to the threshold, but they are still below the threshold, so the algorithm does not raise an alert. So this algorithm has some shortcomings. The IDS may raise many false alarms because it bases its decision on point values. So this is an instant when Di is large. But if we observe the neighboring values of Di for this instant, so the neighboring values are well below the threshold. So this is probably not the onset of a SYN flood attack, because of the randomness in Si and Fi, this Di crossed the threshold, but the neighboring values are all below, well below the threshold. So this is a false alarm where an isolated point has Di above the threshold, but this algorithm 1 raises an alert at this instant. So at time 16, in this figure, the value of Di rises to 102, that is shown here. This triggers an alarm. But this alarm is unwarranted because the Di values at neighboring points around 16, they are well below the threshold tau 1. So this is a false alarm which is raised by algorithm 1. So hence it has this algorithm 1 has this shortcoming. A modest spike in Di at just one point is unlikely to result in memory exhaustion, but it causes the IDS to raise an alarm. So at time 16, the Di value is above the threshold, but since the neighboring points have Di well below the threshold, it is unlikely to exhaust the memory resources of the host. So hence it's not a SYN flood attack. So yet it causes the IDS to raise an alarm. And conversely, the IDS may fail to raise alarms when an attack occurs. So in this example, the value of di between time 28 and 33, which is shown here, this is 28 and 33. So these values are just below the threshold tau 1. So the cumulative effect of the attack packets across this interval, that is 28 to 33, will result in memory exhaustion, but the algorithm does not raise an alarm. This is a false negative. There is actually a SYN flood attack ongoing, but the algorithm fails to detect it. So this is a false negative. So thus this algorithm 1 suffers from false positives like at time 16, as well as it suffers from false negatives, such as between times 28 and 33. So hence we need improved algorithms. So another algorithm is this. We don't consider point values of di, but we average out the values of di. So algorithm 2 raises an alert if the exponentially smooth average of the values of di exceeds the threshold. So exponential smoothing is one way of taking averages. It assigns high weights to recent values of di and low weights to old values of di. So it is calculated in the following manner. Let Si be alpha di plus 1 minus alpha Si minus 1, where alpha is a number between 0 and 1. For example, alpha equals 0.4. First S1 is calculated from D1 and S0, and then S2 is calculated from S1 and D2, and so on and so forth in this way. A simple exercise is to write down the values of S2, S3, S4, and so on. You can express S2, S3, S4, S5, and so on in terms of D1, D2, D3, D4, and D5, and so on and so forth. So you can see that Si assigns higher weights to the recent values di and low weights to the older values, such as di minus 1, di minus 2, and so on. So this is exponential smooth averaging. An alarm will be raised if Si is greater than some threshold tau 2. In this case, we don't focus on a single value of di, but we average it and then raise an alarm only if the average value is greater than some threshold tau 2. So this value of tau 2 is set based on empirical data. So there is a trade-off in setting the value of tau 2. If tau 2 is set too low, then it will result in a lot of false positives, and if conversely tau 2 is set too high, then it will result in a lot of false negatives. So another design parameter is alpha, which is used for computing exponentially smooth average. So if alpha is too close to 1, then we can see here that this di is assigned a high weight of close to 1. Then it will give disproportionate importance to the most recent value of di. But if alpha is close to 0, then the weights assigned to all values of di are even. So if alpha is close to 0, then it assigns roughly equal weights to the recent values of di and old values of di. So this is another parameter that has to be carefully designed. So this algorithm overcomes the shortcomings of algorithm 1 since it uses averaging. So it reduces the number of false positives and false negatives compared to algorithm 1. So for example, at time 16, this value of Si will not be very high because the neighboring values of di are low. So Si will be low and likely it will not cross the threshold tau 2. So hence an alarm will not be raised at this point 16. Whereas in this interval 28 to 33, since di values are high for several consecutive time instants, so Si will be high and likely it will be more than the threshold tau 2. So there will be no false negative in this interval. So the IDS will raise an alert. Let's consider another alternative algorithm which also overcomes the shortcomings of algorithm 1. So algorithm 3 is the following. we define a modified cumulative sum of the previous values of di and raise an alert if this value exceeds the threshold. So during normal operation, the number of fins will balance the number of sins, and hence di equals si minus fi by fi will be close to 0. Let u be an upper bound on the mean of di during normal operations. So di prime is defined to be di minus u. So di prime should be less than or equal to 0 in normal operation, but if di prime is greater than 0, then that indicates that there is possibly a sin flood attack. Let mi be mi minus 1 plus di prime plus, and m0 is 0. So this plus operator is defined in the following way: x plus is defined to be equal to x if x is positive and it is 0 otherwise. So this plus operator prevents mi from going negative. So if mi is going negative, then it is capped to 0. Mi is just the sum of the previous iteration value mi minus 1 and di prime, but it is not allowed to go below 0. So that is done using this plus operator. So mi is computed in this way. The IDS sounds an alarm at the end of the jth interval if mj is greater than tau 3, where tau 3 is a threshold that is determined empirically. So intuitively, if a lot of di primes consecutively are high, in that case mi will cross the threshold tau 3 and vice versa. So this figure shows mi versus time with tau 3 equals 150. So this is the threshold 150, and time is on the x-axis and mi is on the y-axis. So in this figure, the threshold, so the value u is 40 in this example. So di prime is the difference between di and u. So in this case, di prime is negative, and here di prime is slightly positive. Here di prime is a large positive number, and in this interval again di prime is positive. Here di prime is negative, and so on and so forth. So this is the corresponding mi that is calculated using this equation. So it is just a cumulative sum, but the sum is not allowed to go below 0. So between time 2 and 6, di is slightly above u, so that is in this interval. So mi increases monotonically. So we can see the increase here. So mi is increasing in this interval. Between time 7 and 12, di falls below u, so that is this interval. So mi decreases to 0 and remains at 0. So that is shown in this interval. Between time 27 and 33, that is this interval, di is consistently above u. So we can see that from here. So di is above u, so hence di prime is a large positive number. So di is below the threshold tau 1 equals 90 of algorithm 1. So hence there was a false negative in algorithm 1. So this causes mi to increase. So since di is consecutively above the threshold u, so that causes mi to increase and it overshoots the threshold of tau 3 equals 150. This causes an alarm to be raised. So this is a true positive because of the cumulative buildup of SYN attack packets. So here for a large interval, the di values are very large. So it is indicative of a SYN flood attack. So it is likely that actually a SYN flood attack is happening, and hence mi crosses the threshold of tau 3 equal to 150. We can see that here. So this is mi, and it crosses the threshold of tau 3 equals 150 at this point, and the IDS raises an alert. So here in this interval, di crosses the threshold of algorithm 1 at only one point, and here we can see that mi is below the threshold of tau 3. So there is no alert raised by the IDS. So there is no false positive for algorithm 3 at this point, even though there is a false positive for algorithm 1. So in this way, false positive and false negatives encountered with algorithm 1 are avoided with algorithm 3. So we can see that algorithm 2 and algorithm 3 are better algorithms than algorithm 1. So these three are algorithms for DDoS detection. So, in summary, we discussed different methods for detection of SYN flood attacks. So, these methods use the fact that in normal operation the number of SYN packets and the number of FIN packets should be roughly the same. So, we designed different algorithms which keep track of the difference between the number of SYN packets and FIN packets, and these algorithms helped us to detect distributed denial of service attacks. And once these SYN flood attacks are detected, then actions can be initiated to defend against them. So, in that way, these algorithms can be used. So, this concludes our discussion of firewalls and intrusion detection systems. Thank you.